Hi everyone, welcome to part 2 of lecture 7, and in this lecture we will discover normal distribution, or it is called the Gaussian distribution. So the normal random variables play an important role in broad range of probabilistic models. Please note that you will see this distribution in many different classes and in real life. So I suggest you to watch this video a few times if you don't understand the concept of normal distribution, because it's important to understand the basic foundation of that distribution. Okay, so we can use that normal distribution in a variety of fields like engineering, physical, and statistical context. And this distribution, as I say, will be commonly seen in, especially in the statistic class. So before going to the details, let me give you an example to understand the basic idea or the basic foundation of the normal distribution. Let's say we will gather some sample from Turkey. So we will look every single person and we will record the weights of the person. So what do you expect? Like, do you expect something like majority of the people will weigh more than 200 kilograms? Okay, let's say this is a range, and we will put the weights for each person. Let's say this is a 200 kilograms, and let's say this is a 5, or let's say 40 kilograms. And we will record the weights of the adults, right? Okay, adults. Do you expect that the majority of the people will weigh than 200 kilograms? No, right? Maybe a few percentage of those people will be weighter than 200 kilograms, right? And also, a few percentage of the people will weigh less than 40 kilograms. So you don't expect something beyond these 2 points. Okay, if that happens, that's mean the unusual something occurred. So probably the majority of the people will fall into this range, this part, right? Because these things is the normal one. There is nothing unusual here. So the basic foundation of the normal distribution is coming from this idea. So what I mean, in an experiment, everything will be normal. There will not be anything unusual. Okay. So this is actually the main logic or the main foundation of the normal distribution. But to make it more concrete, please watch the following videos and then we will continue. So as you see that in that physical system, just a minority of the balls falls into the sides, right? Sides of that shapes in the right side and the left side. And the majority of the balls just fall to do some area on the middle, okay? So this is how we can think the normal distribution in the real life. So let's continue. there's a useful property of normal distribution is that whenever a random experiment is replicated many times, the average of the results over those replicates tend to have a normal distribution. So what I mean, let's say you are doing an experiment and this experiment associated with some random variables, and let's say that random variables is said to have a Poisson distribution or another distribution. If you repeat this experiment many times, and the averaging of those random variables in each experiment, and then all those averages tend to have a normal distribution. What I mean in terms of math point of view, the sum of large number independent identically distributed random variables has an approximate normal CDF, and regardless of the CDF of the individual random variables. Okay, no matter the CDF of the random variables, if you repeat that process, that experiment, and averaging of the results uh, will tend to have a normal distribution. Okay, so a continuous random variable x is said to be normal or Gaussian if it has a PDF of the form such that exponential function. Okay, so this is the PDF of the normal distribution. So we use the notation x has the normal distribution with the parameter mu and the sigma square. So this is the mean and this is the variance. So the normal distribution has two parameters. The first one is mu and the second one is sigma squared. So if you remember to say that that is a proper PDF, that should satisfy some properties, right? The first one is, let's say, which is the non-negative one. So if you look at this PDF, you will easily see that this is a non-negative because this is positive, positive, and this is squared. That's positive, so the result will be the positive. And another one, and maybe the important one, that PDF should satisfy the normalization property. Remember that was the accumulating all the probabilities should end up with 1. Okay, in other words, sum of all possible probabilities will be equal to 1. So you can safely skip this part, the proof of that normalization property of the normal distribution. You can just skip that one. It is a little bit confusing, but for those who are interested to learn the proof of this property, these axioms, they will find an supplementary videos at the end of this series. Okay, so please just take my words, and accumulating all the probabilities of a normal distribution will end up with 1. Okay, so that's why this PDF is a proper probability density function. So again, this is this is similar to this one. We just continue to here, so you can again safely skip this part, but just you can be sure that the given PDF is a proper one. Okay. So so as I said here, if you wonder how we get the 1, you will find a supplementary videos at the end of the series. Okay, but no matter if you don't watch it, because you will not use the proof through this class. Maybe also you will not use the proof of this one in another class. You just need to know that the given PDF is a proper one. So we say that the normal distribution has two different parameters. The first one is the sigma square, which is the variance, and the second one is the mean. Okay, so let's look at how these parameters change the shape of the normal distribution. Look at the first one. In this one, we didn't change the mu. So this and this distribution, these two normal distribution have the equal mean, the same mean. We just play with the variance. In the first one, the variance is 1, and in the second one, the variance is 4. So if you notice that the changing or increasing the variance will cause more spreading shape, right? So it will spread through the wings, through the right and left side, but decreasing it will give you much more narrower shape. Okay, so we expect that because the increasing variance. Remember that the variance is how a value vary from the mean, how far that points from the mean. So if that is wider, that means, for example, there will be a point here much more will be much more far to the mean, and in this one the points will be closer to mean. So we expect that one. So because this changed the shape of the normal distribution, this is called the scalar or scale scalar parameter. And when we change the mean of the distribution, let's say the variance is 1, the variance is 1, we just changed the mu, the mean of the normal distribution, which was the 5, and now that is 15. In this case, the shape of the normal distribution will not change, but the location of that normal distribution will change. From this region, it will move to this region. So that's why we can call the mu as a location parameter. Okay. Well, as you remember from the previous lectures, we can derive the CDF, the cumulative distribution function, from the PDF, right? And vice versa. How we can do that in the continuous case? We can just integrate the PDF of the distribution over all possible values, right? But in normal distribution case, this guy, the PDF, the integration of the PDF is not possible. So that function, the PDF function, is not integrable. That's why we cannot use we cannot use that rule. We cannot derive the CDF from the PDF. But of course, there's a solution, and you will see that we can solve this integration numerically. What I mean, let's say this is the PDF of the normal distribution, okay? And what the CDF tell us? It tell us the probability of X will be less than or equal to some value, right? And let's say this is the sum value. If we can integrate, that's easy. We can find the area of this region, the left side of that values, which is the X. But because that is not integrable, we can simply put some rectangular, all this region, like small rectangular, okay? And if we calculate the area of them and sum of all possible rectangular, we will find the probability, because the probability means that the area between this line, okay? So that's why for the CDF of the normal distribution, you will find a table. It is, I'm gonna show that table, and you will use that table to calculate the CDF of the normal distribution. In other words, if you are asked what is the probability of X less than or equal to some value, you will find this value on the table, and the probability will be given to you. Okay. So the expected value is mu, the mean, because the PDF is symmetric around the mu. What I mean, let's say this is the mu, What I mean, the area of the left side of that mu will be equal to right side of that. Okay, so the PDF is symmetric. And the variance, as we said, is the sigma square. Again, there is the proof of the variance. You can again safely skip that part. But for those who are interested how to prove that one, there will be some supplementary videos at the end of this series, okay? So the variance of the normal distribution is sigma squared. What we learned so far, the PDF of the normal distribution is symmetric around the mu, and also the variance is sigma squared. So there is a very useful property of normal distribution, and we can use this property in many different problems. And we title it, but normality is preserved by the linear transformation. Well, what I mean, the f x a random, if x is a normal random variable with mean mu and the variance sigma squared, and if a is not equal to 0 and b are scalars, then random variable y such that a times x plus b is also normal with the mean and the variance. The expected value of y, which is the mean of the y, will be equal to a times mu plus b, and the variance will be the a squared times sigma squared. So why this can happen? Because we can simply we can write this one as a times expected value of x plus b, and the expected value, expectation is the linear operator. That's why we can simply write as in this form. And remember that the variance will not be affected by the constant values. We will just take the coefficient of the x and square it to calculate the variance of the near random variables. Okay? So let's continue with the standard normal distribution. A continuous random variable z is said to be standard normal if it has a PDF of the form like that. In other words, the z is a normal random variable with mu is equal to 0, and the sigma squared, the variance is equal to 1. So in this case, if this is the case, we can say that the z has a standard normal distribution. So which is similar to what we've seen in the previous part, which is a standard uniform distribution. That was, let's say, x has a uniform distribution with parameters 0 and 1. That was a standard uniform distribution, and we use this distribution to define some other distribution, right? What I mean, if y has a uniform distribution with 5 and 10, we can simply write this uniform distribution based on this one. We see that. So same thing here. We can again define a standard normal distribution, and the conditions are the mu should be equal to 0 and the variance should be equal to 1. So what that means, the PDF of the standard normal distribution is symmetric around to z equal to 0, and its CDF is denoted with the letter phi, okay? So this is the notation for the CDF of the normal distribution, the standard normal distribution. And you will see that one the many times when you solve some problems with the normal distribution. So the phi doesn't have a closed form formula, but its value evaluated at the various z values are prepared in the form of table and is available. So I told this before, and we will use this table to calculate some probabilities, okay? So any probabilities actually. So the table for positive z values is enough. Why? Because the PDF is symmetric around the 0, okay? What I mean, let's say this is minus z points and this is a positive z points. This area okay, and this area is equal. Also, this whole area is equal with this whole area. And the summation of all these possible probabilities is 1. So that's why the phi z will be equal to 1 minus phi minus z. Okay, so if this whole area is 1, what I mean that 1 minus phi z, which is equal to phi minus z. Okay, so so this is a standard normal table, and we will see how to use them, but you will find the probabilities for some different values. For example, if the z is equal to 0.41, we can just take this one and this one. So this intersection will be the probability of that point. Let's say this is a z into 0.1, and what we are looking for, the probability of x, it will be less than or equal to x will be equal to this one, this area, and this area is this one, 0.65 something. Okay, this is how we use the standard normal table, but we will I will give you the detail of this table. Later, we will use this to solve some problems. So also we can use this table to calculate some range, some probability of some range. For example, let's calculate the probability of z that will be greater than or equal to minus 1.25 and will be less than 0.37. So for any random variable and a is less than b, we have the probability of x will be greater than a and will be less than or equal to b, will be equal to the probability of x is less than or equal to b minus probability of x will be less than or equal to a. What that means, the CDF of b minus the CDF of a. So let's draw something, and here we have x, any possible x. Let's say this is a, and let's say this is b. What I'm saying, the x will take the values between this range, and I'm asking the probability of this range, right? Because the x will be within this range. So from this part, if I subtracted this part, I will end up with this one, right? So this is the logic of that that formulation. So since z is a continuous random variable, inclusion or exclusion of the endpoints of the interval do not matter. We just seen that in the previous classes. And so we can calculate the ask probability as the probability of this one, the z will be in this range. We are asked this one, such as the phi, the CDF, the phi of 0.37 minus phi minus 125. First, let's look at what these values in the distribution. Let's say this is our distribution, and this is the first, the value, which is actually the b, okay? It's actually the b. And this is the second value, and this is actually a. What we did here, from the left side of b, if we subtract the left side of a, you will get this region. Okay, So, okay, let's say I have the table only for the positive values. Okay, only for the positive values. So what I mean, I had to rewrite this part as we shown in here, right? So that's mean the pi minus 25, 125 is actually equal to 1 minus pi 125. Okay, so let's rewrite this as this one, and that's mean the pi 0.37 plus pi 1.25 minus 1. So uh, we just expand this multiplication. So let's look at the table to find the probabilities of these guys, which the first one is 0.37. Let's say this is a um, 0.3, and this is a 0.07. And the intersection of these two guys, so the summation of this one and this one will give us the 0.37. Okay, this is what we are looking for. And the intersection will give the corresponding CDF value. Okay, this one. So let's look at this one, 1.25. Okay, 1.2 here and 0.05 here. So if I sum these two guys, I will get what I'm looking for, 125. And the intersection of these guys will give me the CDF of this one, okay, which is 0.89 something. So I just put these values in this summation, and I will end up with 0.53 something. What that means, the probability of X, or probability of Z, will be within this range is 0.53 something. Okay, this is how we use the standard normal table. So actually, this is what I did so far. And well, the standard normal table is not only useful for the parameters 0 and 1, but we can use it for any normal random variables with parameters mu and the sigma square. So remember that the linear transformation preserves the normality. And that is very useful property, because thanks to this property, we can convert any normal random variables into the standard normal form. So, but how we can do that? Let X be a normal random variable with mean mu and the variance sigma square. We can standardize X by defining a new random variable Z as follows. So the Z will be equal to X divided by sigma minus mu divided by sigma. And this is equal to X minus mu divided by sigma. So this is any normal random variables. And if we do this calculation, we will convert it into the standard form. So since Z is a linear function of X, the Z is normal too. And also the expected value of Z will be equal to the expected value of X minus mu divided by sigma squared will give us the 0, because we convert X into the standard normal form. And also the variance of Z will be equal to the variance of X divided by sigma squared, that will be equal to 1. Okay, that's why we can say that as a result, the Z is a standard normal random variables. This allows us to calculate the probability that of any event defined in terms of X the parameters is not 0 and 1, we can redefine the event in terms of z, and then we can use the standard normal table. So let me give you an example. The annual snowfall at a particular geographic location is modeled as a normal random variable with the mean of mu is equal to 60 centimeter and the standard deviation of sigma is equal to 20 centimeters. So what is the probability that this year's snowfall will be at least 80 centimeters? So first, let me draw before going to the solution. Let's say this is a normal distribution of x, and the mu is equal to 60 centimeter, and this is the x value. And what is the probability that this year's snowfall will be at least 80 centimeters? That means it will be greater than or equal to 80 centimeters. So this area, right? And x has the normal distribution with the parameters and 20, right? So, and what we need is that to convert this normal distribution into the standard form. So what we are asked, the probability of x will be greater than or equal to 80, right? And how we can transform this one into the standard form, that is simply x minus mu divided by sigma. So instead of x and these values, we can write the x minus 60, this is mu, divided by 20, this is sigma, will be greater than or equal to 80 minus 60 divided by 20. So x will be z, and these values will be the corresponding values in the standard form, and this is equals to 1. So what I ended up with, actually I'm asking to probability of z will be greater than or equal to 1. Okay, now this is equal to this one, right? Because let's say this is a graph, and let's say this is a 1, this is a mu, which is equal to 0, and I'm asking this part, and in the table, in the positive normal table, I'm giving to left side of that particular value, right? So I'm giving this one in table. So how can I find this one? The total area is 1, and I'm giving this part, which is, let's say, the a. 1 minus a will give us to this part. Let's say this is b. So the same logic here. So this is equal to 1 minus probability of z will be less than 1. So, and what I'm gonna look, which is equal to phi 1, and let's look at the phi 1 values in table. So this is 1 and this is 0. The sum is 1, and the corresponding the area, the probability is 0.84 something. So 1 minus the probability of 1 minus phi 1 is equal to 0.15 something. So the area of this region, in other words, the probability of z is greater than or equal to 1 is equal to this value. Okay, it's equal to this value. So this is how we use the standard normal table for any random normal variable. Okay. This is the end of part 2. Thanks for watching, and we will continue.